The next talk is a lighting talk by Hiroyasu Tajima. So please, Hiroyasu, go ahead.
Yeah, thank you. Thank you very much for your introduction. And today's talk is based on this paper with Ken Funo at Weekend. Oh, sorry. Oh, sorry. So something. Oh, okay. Now it works.
Yes.
This is him. And this paper is selected as editor's suggestion and featured in physics. Let's start. First of all, let's see the purpose of today's talk. The purpose is to clarify the coherence effect on the trade-off relation between current and dissipation. Here, current means heat current or electric current or something, and dissipation means entropy production. And in physics, there are many trade-off relations between these two. For example, in Joule law, if we want to make current large, then we have to allow the dissipation. So heat production must be also large. And recently, rigorous trade-off inequalities have been derived in these various researches. And these various trade-off inequalities have many forms, but message is clear. Large current causes large dissipation. And these trade-off inequalities also have various applications, including the power efficiency trade-off on heat engines. Our purpose is to clarify the coherence, how coherence affects these trade-off. To achieve this goal, we focus on the current dissipation ratio, the ratio between the heat current and entropy production rate. J is heat current and sigma dot is entropy production rate. This ratio corresponds to the inverse of the resistance in heat current. To see that, let's see the Joule's law. In Joule's law, the inverse of resistance is described as like this. Here, this is electric current, and this is heat production. This has the same structure as the current dissipation ratio. Here is heat current, and this is electric current, and this is entropy production, and this is heat production. So we can interpret the current dissipation ratio as the inverse of resistance in heat current. For this quantity, we derive three results. The first result is that coherence between different energy eigenspaces decreases the ratio. In other words, this type of coherence enhances the resistance of heat current. And the second result is coherence between degeneracies enhances this ratio. Namely, this type of coherence weakens the resistance. The third result is the dissipationless current. When the coherence between degeneracies is large enough, macroscopic heat current without dissipation can occur. Namely, the resistance vanishes effectively. Now, let's see the details of our results. We firstly introduce our setup. Our setup is an open quantum system obeying the standard master equation. And here, this is dissipation term, this is jump operator, and this is jump rate, which satisfies the detailed balance. And we also define heat current and entropy production in standard way. This is heat current, and this is entropy production. And to clarify the coherence effect on the ratio, we give two classes of coherence. The first class is the coherence between different energy eigenspaces, and the second one is coherence between degeneracies. To do so, we take energy eigenstates. Here, E is eigenvalue, and J is degeneracy number. And we define these two states from law. low is an arbitrary state of the target system. And here, pi e is the projection to the energy eigenspace of E, and pi ei is projection to EI, state EI. Then the low BD becomes block diagonalized state in which coherence between different energy here is removed, while the coherence between degeneracy here and here still remains. On the other hand, in the low SD, strictly diagonalized state, all coherence is removed. Because all coherence in low BD is equal to the coherence between degeneracies in low, it is useful to measure this. So we introduce a measure of coherence. This is the measure. This is the L1 norm of coherence, which is a standard resource measure in the resource theory of coherence. So we use it to measure the coherence between degeneracies in low. This is equal to the coherence between degeneracies in low. Here, let us see our main result. The first result is this inequality. This inequality shows the current dissipation ratio for low is always smaller than that of low BD. So, the coherence between different energy here always enhances the resistance of heat. Please remark that this quantity, this ratio corresponds to the inverse of the resistance of heat. And the second result is lubrication. It is shown by these two inequalities. This inequality shows the limitation without coherence because this is an upper bound for the ratio for low SD, strictly diagonalized state. And the second inequality is an upper bound for the ratio for low BD. And the difference between these two is here. Here is the coherence term because this term is in proportion to coherence between degeneracy. This is written as this, and this term is the L1 coherence norm of low BD. So this is amount of coherence between degeneracy in low. And because of this, we can derive, we can see this is smaller than this. So the upper bound of this is, can be strictly larger than this. And it means coherence between degeneracies can decrease the resistance of heat. And we can see the quantum lubrication effect in a concrete model. Let's see the model. This graph is a numerical simulation on super radiant 2 qubits. And in this graph, this is here. And this upper bound for, without coherence is here. And this is here red line. And this is here black dotted line. So the current dissipation ratio for low is strictly larger than this classical bound. So and now we can see quantum lubrication actually happens. So the next question is to what extent we can enhance this effect. To see that, let us assume AQM becomes the order of n square. So here, order n square. Then this inequality, our main result, one of our main results, allows this ordering, which means J is in order of n, but the entropy productions remains order of 1. So this means a macroscopic dissipationless current. We can see this dissipationless current in a concrete model. This is the model. This model has n ground states and n excited states and collective jump between them. Then we can we can prepare some state which satisfies this dissipation-less current actually. And with using this dissipation-less current, we can achieve the Carnot efficiency with finite power effectively. The effective means this efficiency is very close to Carnot efficiency. This is the difference. This is very small. And at the same time, we can achieve the power within order of n. Now we finish my talk. So sorry, I finished my talk. We study the coherence effect on the current dissipation ratio. Our results is summarized into 3 rules: quantum friction, quantum lubrication, and dissipation-less current. Thank you very much.